True engineering mastery isn't about memorizing API documentation. It's about building the mental models that make those documents redundant. This grid represents 21 foundational concepts. Together, they form a unified system for managing asynchronous work. At the base, a coroutine is simply a task that can pause its own progress and resume later. Suspension is the mechanic that allows this. It's a pause that doesn't freeze the underlying system thread. Managing this pause and resume cycle is how an application scales. It allows thousands of tasks to operate simultaneously without exhausting system resources. When a paused task resumes, it continues exactly from its saved state. It doesn't need to restart the operation from the beginning. The suspend keyword acts as the permission for that pause to happen. It is a signal of capability, not a mandatory stop command. To maintain this state, the system uses a continuation.
Think of it as an internal bookmark that saves every variable and execution point. You trigger this work using builders. Launch initiates a background task you don't need a result from, while async starts work that returns a value later. These combined tools give you surgical control over background execution. You decide exactly where work starts, where it pauses, and what it returns. This diagram shows a scope. It is the boundary that owns coroutines and dictates how long they are allowed to run. Every coroutine in that scope has a job. This is the specific handle you use to track its status or manually cancel the work. This hierarchy enables structured concurrency. A parent process will automatically wait for all of its child tasks to finish before it marks itself as complete. You control this waiting period with builders. CoroutineScope politely suspends until children finish, while the runBlocking builder halts the entire underlying thread. Without these boundaries, untethered background tasks continue to consume memory long after they are genuinely needed, leading to application instability. If a single task fails, a SupervisorJob acts as a failsafe. It prevents a single child's error from cascading and crashing the entire parent process. This diagram shows dispatchers. They route coroutines to the specific system threads best suited for the work. The main lane is for UI updates. I/O is for networking and database delays. The default lane is reserved for intense mathematical calculations. The with context function safely allows a running coroutine to switch between these specific system lanes mid-execution without dropping the task. Precise dispatcher selection ensures heavy background processing never competes for resources with the UI. The application stays responsive because the work is happening in the right lane. When you stop a process, cancellation is cooperative. The system requests the coroutine to stop, but the code itself must check for that request. If a coroutine must finish a critical task during shutdown, non-cancelable provides a brief window to execute final cleanup operations. A cancellation exception is a routine procedure, like closing a file. It's distinct from a standard exception, which indicates an unexpected failure. Uncaught exceptions propagate upward through the hierarchy. This diagram shows how a SupervisorScope acts as a containment wall, stopping the failure from spreading further. This isolation transforms potentially fatal crashes into managed incidents. You aren't just catching errors, you're containing them. Even your choice of builder changes how failure is handled. Launch exposes exceptions immediately, while async holds them until you explicitly ask for the result. This diagram shows how these 21 concepts interlock. They aren't just separate tools, they are the architectural components of a single functional system. When you view coroutines through these models, you can predict how a system will behave before you write a single line of code. Next, we apply this architecture to data streams in our